There is a kind of star in the sky tonight. Most people walk past without knowing what they're seeing. Small, faint, no fusion left inside it at all, just cooling, the way a coal cools once the fire is out, and it will keep cooling longer than the universe has so far existed. This is what a sun-like star looks like once it's finished, not destroyed. Finished. Ours will look like that too, not as a metaphor, as a measurement. A star with the sun's mass ends up roughly Earth-sized while keeping most of its original weight, so a teaspoon of it would outweigh a small car. Tonight is about the sun as it will be. Ordinary, dim, one more point of light among billions. If you enjoy falling asleep to stories about the universe, you might want to subscribe. We've got plenty more nights like this waiting for you. Now, let's get started. For most of human history, nobody could explain why the sun was hot. That sounds like a strange thing not to know, given how much depended on the answer. But until the early 20th century, nobody had a mechanism that actually worked. The obvious guess was fire, ordinary burning, the same chemistry that keeps a candle lit. Chemists worked out early on that if the sun were simply combusting like a lump of coal, it would burn through its entire mass in a few thousand years. The sun is older than that. Geologists already knew the Earth was hundreds of millions of years old at minimum, so combustion was ruled out almost immediately, and physics was left with a hole where an answer should have been. The next best guess came from Lord Kelvin, one of the great physicists of the 19th century, who proposed that the sun was slowly collapsing under its own gravity, and that the collapse itself was releasing heat. It's a real physical process. Contracting gas does warm up. Kelvin ran the numbers and arrived at an age of perhaps 20 or 30 million years for the sun. It was a respectable calculation from a respectable man, and it was wrong by a factor of more than 100, though nobody knew that yet, because nobody had anything better to put in its place. Kelvin's number quietly poisoned other fields too. Geologists studying rock layers, and biologists trying to fit Darwin's slow evolutionary timescales onto a 30-million-year-old sun, spent decades arguing with a figure that was simply incorrect and had no way of proving it. The replacement came from a British astrophysicist named Arthur Eddington, and it arrived in a single afternoon in August of 1920 in a lecture hall in Cardiff, Wales. Eddington was addressing the British Association for the Advancement of Science, and he had recently seen the work of a chemist named Francis Aston, who had been carefully weighing atoms. Aston found something odd. 4 hydrogen atoms, added together, weighed very slightly more than a single helium atom. Not much more. A difference of about 0.7%. But Einstein had shown a few years earlier that mass and energy were the same thing, wearing different clothes, and a small amount of missing mass, multiplied by the speed of light squared, is not a small amount of energy at all. Eddington did the arithmetic in front of his audience. If the sun were converting hydrogen into helium, losing that 0.7% as pure energy in the process, it wouldn't need to burn anything. It would simply need to keep converting one element into another, quietly, at its core, for billions of years. He proposed this almost as an aside, one plausible answer among several he was weighing, and he ended the lecture with a line that reads, "Today, less like physics and more like prophecy," that if this subatomic energy really was what powered the stars, humanity might one day learn to control that same power for itself. He was speaking 19 years before the first nuclear reactor existed anywhere on Earth. Eddington didn't have the mechanism. He had the bookkeeping. He knew mass was disappearing and energy was appearing in its place, but he couldn't say exactly how hydrogen became helium at the level of individual particles. That took another physicist, working 19 years later. In 1939, Hans Bethe worked out the actual sequence of nuclear reactions, now called the proton-proton chain, that fuses hydrogen into helium inside a star like the Sun. Bethe later admitted he'd worked much of it out to win a bet with a colleague over who could finish the calculation first. He won the Nobel Prize for it in 1967, almost 30 years after the fact, once the rest of astrophysics had fully absorbed what he'd done. For decades after Bethe, the theory stood on paper. Nobody had actually caught the Sun in the act. That changed, or at least it was supposed to, with an experiment that still counts as one of the strangest in the history of astronomy. In 1965, a chemist named Raymond Davis began building a detector inside the Homestake gold mine in Lead, South Dakota, nearly a mile underground, buried that deep, specifically so that cosmic rays from space couldn't interfere with what he was hunting for. The detector itself was a tank holding 100,000 gallons of ordinary dry cleaning fluid. Fusion in the Sun's core releases, alongside energy, a flood of nearly massless particles called neutrinos, and every so often, roughly one every few days, a neutrino would strike a chlorine atom in that tank and turn it into a detectable form of argon. It was an absurd way to look at the Sun. A tank of cleaning solvent in an abandoned mine, waiting for a subatomic particle to leave a single radioactive atom behind once or twice a week. And yet it worked. Davis detected solar neutrinos. The Sun really was fusing hydrogen, exactly as Eddington had guessed and Bethe had calculated. Except the numbers didn't match. Davis was catching about a third of the neutrinos the theory predicted, and for close to 3 decades, nobody could say why. Some suspected an error in the solar models. Others suspected an error in the detector. Davis rechecked his own experiment for years and found nothing wrong with it. The resolution, when it finally came in the late 1990s, turned out to be stranger than either possibility. Neutrinos change identity in flight, shifting between types as they travel from the Sun's core to a mine in South Dakota, and Davis's detector had only ever been built to catch one of those types. The Sun had been fusing hydrogen at exactly the predicted rate the entire time. The mismatch was never in the Sun. It was in what neutrinos turn out to be. Davis shared the Nobel Prize in 2002, at the age of 87, for an experiment that took 37 years to be fully understood. What all of this adds up to is a Sun that runs on a clock, and not a metaphorical one. An actual, countable supply of hydrogen, converting into helium at a fixed, measured, independently confirmed rate, inside a core about the size of Earth, repeated a few 100,000 times over. Every second, the Sun turns roughly 600 million tons of hydrogen into helium. In human terms, that is more mass than every ship ever built by every navy in history, converted every single second, and it has been running at close to that rate for 4.5 billion years already. That number, 4.5 billion years, comes from a different kind of evidence entirely, not from watching the Sun at all, but from cutting open rocks that fell from space. Meteorites, the oldest unaltered material in the solar system, contain radioactive elements that decay at fixed, known rates, and when scientists measure how far that decay has progressed inside the oldest meteorites ever found, the number comes out consistently to around 4.6 billion years. That's the age of the whole solar system, the Sun included, and it lines up with the independent stellar models built from Eddington's and Bethe's physics. 2 unrelated methods, one from geology, one from nuclear astrophysics, arriving at the same figure. That kind of agreement is about as close as science gets to certainty. Here's the part that took me the longest to sit with, the first time I actually worked through what it meant. The Sun is not young, it's not old either. It sits almost exactly, eerily, at the midpoint of its working life. Halfway through the fuel, halfway through the fusion. We happen to evolve on a planet orbiting this particular star during the one stretch of its multi-billion-year existence when it is neither newly formed nor visibly failing. There's no law of physics that required that. It's simply where we landed. Stars burn through their hydrogen at a rate set almost entirely by their mass, and the Sun's mass puts its total main sequence lifespan, the stretch where it fuses hydrogen calmly and steadily, at somewhere close to 10 billion years. Not all stars get that long. A star noticeably heavier than the Sun burns hotter and faster, and can exhaust itself in tens of millions of years instead of billions. A star noticeably lighter sips its fuel so slowly it could still be fusing hydrogen when the universe is many times its current age. Mass decides the budget. The Sun's budget happens to be generous enough that a slow chemical process, like the evolution of life on a nearby rocky planet, had room to actually happen before the terms of the arrangement changed. There's a strange detail about that fusion that most explanations skip past, and it changes how you think about sunlight itself. A photon born in the Sun's core doesn't simply fly outward and reach us 8 minutes later. It's true that the final stretch, once light leaves the surface, does take about 8 minutes to cross the 93 million miles to Earth. But before that, inside the Sun, the same photon's energy has to fight its way out through matter so dense that it travels only a fraction of a millimeter before being absorbed and re-emitted in some new random direction, over and over, in what physicists call a random walk. A 1992 calculation published in the Astrophysical Journal put the average time for that energy to diffuse from the core to the surface at around 170,000 years. In other words, the warmth landing on your skin tonight, if you were standing in daylight, began its journey inside the Sun sometime before modern humans existed as a species, and only spent the last 8 minutes of that journey actually being what we'd call light. If you have fallen asleep to this channel before, welcome back. And if this is the first time, what I'd ask you to sit with tonight is simple. Everything warm about this solar system, every ray of light that ever reached a leaf or a retina, comes from that one bookkeeping trick Eddington glimpsed in a lecture hall in 1920, and Davis caught in the act, decades later, in a mine a mile underground. Mass quietly becoming energy, 4 hydrogen atoms losing a sliver of themselves to become 1 atom of helium, over and over, 600 million tons a second, for 4.5 billion years, with about the same span left to run. If you have ever wondered what actually happens when that budget runs out, and what the Sun becomes once it does, that's the rest of tonight. Somewhere around 5 to 6 billion years from now, give or take, the Sun runs out of something it has never run out of before. Not fuel entirely, just the hydrogen sitting in its core, the specific volume of gas hot and dense enough for fusion to happen at all. The rest of the Sun, the outer layers, will still be almost entirely hydrogen, but the core, the one region where pressure and temperature are high enough to force protons together against their own repulsion, will have converted nearly all of its hydrogen into helium. One detailed model of the Sun's composition puts the core's makeup right at the end of this hydrogen burning phase, at roughly 11% hydrogen and 87% helium by mass, a near-total reversal of what it started with. And helium, at the temperatures the core has reached by then, doesn't fuse. It just sits there, inert, a kind of ash the fire can no longer burn. This is the part that's easy to misunderstand, because it sounds like the story should end there. It doesn't. What happens next is stranger than running out of fuel. The core, no longer generating enough outward pressure to support the weight of everything above it, begins to contract under its own gravity. That contraction is not a slow fade, it's a compression, and compression heats things up. As the helium core shrinks and its temperature climbs, a thin shell of hydrogen just outside the core, hydrogen that was never hot enough to fuse before, suddenly finds itself hot enough. Fusion doesn't stop, it moves. The Sun goes from burning hydrogen in a roughly spherical core to burning it in a shell, a layer wrapped around a dead, shrinking, increasingly dense ball of helium. For context, this shell-burning phase is not a minor technical footnote. It's the mechanism that turns a calm, stable star into a red giant. The shell burns hotter than the old core ever did, because it's compressed by everything pressing down from above and heated by everything contracting below. That extra heat has to go somewhere, and where it goes is outward, into the Sun's outer envelope, forcing those outer layers to expand dramatically. The Sun doesn't get brighter by burning more efficiently. It gets brighter and larger because its engine has relocated to a smaller, hotter space, and the rest of the star is being pushed outward by the runoff. Astronomers have a name for the star during this transition: a subgiant. It's an underused word outside the field, but it names something real, a star that has left the main sequence and started expanding, without yet becoming the swollen red giant most people picture when they hear the phrase. One detailed evolutionary model puts this subgiant stage at roughly 700 million years long for the Sun, the core quietly shrinking and heating, while the outer layers slowly begin their expansion. It's not fast, measured against a human life, but against the 10 billion years the Sun spends calmly on the main sequence, 700 million years is a genuinely brief transition, over almost as soon as it starts by the star's own clock. Once the helium core has contracted and heated enough, the hydrogen shell burning around it kicks into a much higher gear, and the expansion accelerates. The same model places the true red giant branch phase at a little over 600 million years, faster still than the subgiant stage. And it's the part that gets illustrated most often: an enormous, swollen star, its surface pushed outward until it may reach as far as the orbit of Venus, possibly Earth's orbit, depending on exactly how much mass the Sun sheds along the way, which is one of the genuine open questions in solar physics. What isn't in question is the direction: bigger, cooler at the surface, because that same energy is now spread across a much larger area. Redder, for the same reason, which is where the name comes from, and significantly brighter overall, because even though each patch of surface is cooler, there is vastly more surface radiating it. Mercury and Venus don't get the benefit of that uncertainty. Updated models that account for the Sun's mass loss, the pull of tides between a swelling star and the planets orbiting it, and the Sun's slowing rotation all agree on one point, without much disagreement left between them. Mercury and Venus are almost certainly going to be engulfed outright, swallowed into the expanding envelope as it reaches past their orbits. Earth sits closer to the edge of the uncertainty. As the Sun loses mass through this phase, its gravitational grip loosens slightly, and the remaining planets drift a little farther out in response, which might, by a narrow margin, let Earth's orbit outrun the expanding surface. Whether it does is still genuinely unresolved, an open question researchers are actively modeling rather than a settled fact this script can hand you cleanly. Either way, outrunning the Sun's surface would be a technicality. Long before the swelling reaches anywhere near Earth's orbit, the increase in the Sun's total brightness will have already boiled away the oceans and stripped the atmosphere. Surviving as a planet and remaining a habitable one are two very different questions, and only one of them is genuinely still open. The first time I sat down and actually worked through the timeline of this, what surprised me wasn't the ending. Everyone who has thought about the Sun's death for more than 5 minutes knows, in general terms, that it swells up and becomes a red giant. What surprised me was how much is still happening internally, invisibly, in distinct stages, long before the dramatic swelling becomes obvious from outside. The subgiant phase, the shell ignition, the slow contraction of a core that no one will ever see happen from the surface. Most of a star's real transformation happens in a region no telescope will ever image directly. We infer it entirely from physics and from watching other stars further along in the same process. That's worth sitting with for a moment. We've never watched the sun do this, obviously, because it hasn't happened yet. What we know about this transition comes from two places: theoretical models of stellar structure, built from the same fusion physics Eddington and Bethe worked out, and from observing other stars of roughly the sun's mass that are further along the same evolutionary track right now, scattered across the galaxy in every stage from subgiant to full red giant. Put those observations next to the models, and they agree closely enough that astronomers trust the sequence in detail, not just in outline. The idea that stars even fall into distinct categories like this, main sequence stars and giants, as genuinely separate populations rather than one continuous blur, is itself barely older than a century. In 1911, a Danish astronomer named Ejnar Hertzsprung, working with photographic plates of two nearby star clusters, the Pleiades and the Hyades, plotted each star's brightness against its color and noticed the points weren't scattered randomly. They fell into two distinct groups, one running along a narrow diagonal band, the other sitting apart from it, bright but unexpectedly cool and red. A couple of years later, an American astronomer named Henry Norris Russell, working independently at Princeton with a much larger sample of nearby field stars, found the same split without knowing Hertzsprung had already seen it. Neither man had access to the fusion physics that would eventually explain why the split existed. Eddington's Cardiff lecture was still nearly a decade away. They simply had the data, plotted honestly, and the pattern refused to be smoothed over. That plot, now called the Hertzsprung-Russell diagram, is still the map astronomers use today to place a star like the Sun and see, at a glance, exactly where in this sequence of transformations it currently sits, and where the track leads from here. Eventually, deep inside the contracting helium core, something new happens. As the core keeps shrinking, its temperature keeps climbing, and there is a threshold, close to 100 million Kelvin, at which helium itself becomes capable of fusing. Not into hydrogen, obviously. Helium fuses into carbon through a process called the triple alpha process, in which 3 helium nuclei combine in a short sequence to build one carbon nucleus, sometimes followed by a 4th helium nucleus, fusing onto that to make oxygen. This is, quietly, one of the more important facts in this entire story, because carbon and oxygen are not primordial. They were not present in any meaningful quantity after the Big Bang. Every carbon atom in your body, in the air, in the ink of every book ever printed, was manufactured inside a star, going through exactly this stage, later scattered into space when that star died. The Sun, once it reaches this threshold, will join the long list of stars that have done this before it, quietly assembling the raw material for whatever comes after. For stars around the Sun's mass, helium ignition doesn't happen gently. Because the core has become so dense and compressed by that point, it ignites in what's called a helium flash, an extremely rapid, almost explosive onset of fusion, over in a matter of seconds at the core, even though its effects ripple outward over a much longer stretch of time. It sounds violent, and at the core, briefly, it is. But it doesn't destroy the star. The outer layers barely notice. The flash is a release valve, not a catastrophe. Afterward, the Sun settles into a new, temporary equilibrium, helium fusing steadily in the core, hydrogen still fusing in a shell around it. The star now smaller and hotter at the surface than it was at the peak of its red giant swelling, though still nothing like the compact, stable star it once was. That calmer core helium burning stage is expected to last roughly 100 million years, a long stretch by any ordinary measure, and still barely a tenth of what the main sequence gave it. This is the part that took me the longest to accept, honestly. Not the ending, the middle. The fact that dying, for a star like the Sun, isn't a single event. It's a sequence of distinct, well-defined phases, each with its own physics, each lasting long enough that if you were somehow able to watch from a safe distance, you'd have time to get used to each new version of the Sun before it changed into the next one. Red giant, helium flash, something calmer, briefly, afterward. None of it collapses into a single dramatic moment. It unfolds, the way a long illness unfolds rather than an accident. Each stage legible in the light the star gives off, if you know how to read it. None of this happens to the Sun in isolation, of course. Everything orbiting it experiences the consequences of an engine relocating and a star swelling toward them. And that part of the story, what actually happens to the inner planets once the red giant phase is fully underway, is where the next stretch of tonight is headed. After the helium in the core is used up, roughly 100 million years after it started, the Sun faces the same problem twice over. The core, now mostly carbon and oxygen from all that triple alpha fusion, is once again too cool to burn anything further, and this time there's no third act coming. Fusing carbon requires temperatures near 1 billion Kelvin, roughly 10 times hotter than the helium flash itself, and reaching that threshold takes more gravitational weight bearing down on the core than a star of the Sun's mass will ever have. Stars above about 8 times the Sun's mass can keep contracting and heating their way through carbon, then neon, then oxygen, all the way to iron, building each new fusion stage on the ashes of the last. The Sun simply isn't heavy enough to make that climb. Its carbon-oxygen core will contract again, heat again, and then stop there, permanently, held up not by fusion, but by something stranger, a quantum mechanical pressure from the electrons themselves, resisting being squeezed any closer together, regardless of how hot the core gets. That resistance is what finally halts the collapse for good, and it's also the first real clue to what the Sun's remnant is going to become. It contracts, and once again ignites a shell of fuel around that inert core, except this time there are 2 shells instead of 1, a layer of helium still fusing just outside the carbon-oxygen core and a layer of hydrogen fusing further out still above that. Astronomers call this stage the asymptotic giant branch, usually shortened to AGB, and it is, by most measures, the most violent and unstable period the Sun will ever pass through. The instability comes from the 2 shells not burning steadily side by side. They alternate. The helium shell periodically flares up in what's called a thermal pulse, a sudden runaway surge of fusion that dumps enormous energy into the surrounding layers, pushes the hydrogen shell outward and temporarily shuts it down, then subsides, allowing the hydrogen shell to reignite until enough helium ash builds up beneath it to trigger the next pulse. These pulses recur roughly every 100,000 years, and each one drives a fresh wave of mass loss from the star's outer envelope. It's worth being honest about what this means for the calm, gradual story told so far. This stage does not unfold gently. It convulses, again and again, on a rhythm measured in geological time rather than a human one, but a rhythm nonetheless. Each pulse peeling more of the Sun's outer material away into space. We don't have to take any of this entirely on faith from models either, because there is a star close enough and famous enough that amateur astronomers have tracked it for well over a century. It's called Mira, the prototype of an entire class of stars now named after it, sitting a little over 400 light-years away in the constellation Cetus. Mira swells and dims on a cycle of roughly 332 days, brightening and fading by about 7 magnitudes. Enough of a swing that it goes from being invisible to the naked eye to being one of the more obvious stars in its patch of sky, and back again, over and over. a rhythm regular enough that observers have been logging it since the 17th century. Mira is losing mass into space right now, continuously, at a rate astronomers have actually measured from the glowing shell of gas and dust expanding around it. It is, essentially, a live demonstration of the exact stage the Sun is going to pass through, 5 billion years early, conveniently placed close enough for a backyard telescope to catch. What makes this stage matter beyond spectacle is a process called dredge-up. Between thermal pulses, the boundary of the star's convective envelope can reach down deep enough to stir material that was fused in the shells, carbon especially, up to the surface, where stellar winds can carry it off into space entirely. This is, in human terms, the mechanism by which a star hands back the elements it spent its life assembling. Every AGB star that has ever lived has done this, seeded the space around it with freshly made carbon and other heavier elements, which is part of why the carbon in your body didn't have to come from the Sun specifically. Older stars did this same thing, in this same stage, long before the Sun or Earth existed, scattering the raw material that eventually became us. The mass loss during the AGB phase is not a minor trickle. Over its course, a star like the Sun can lose somewhere in the range of half its total mass, expelled gradually through stellar winds and violently through the thermal pulses, until there simply isn't much envelope left to lose. Researchers studying stars in this stage put the entire process, from the first thermal pulses to the final stripping of the envelope, at something on the order of 200,000 years, a genuine blink relative to the 10 billion spent quietly fusing hydrogen before any of this began. What remains, once the outer layers have been stripped away nearly to the core, is a hot, compact, exposed stellar remnant, still glowing at tens of thousands of degrees, surrounded by the cloud of everything it just shed. That cloud is the part most people have actually seen, even if they didn't know what they were looking at. It's called a planetary nebula, and the name is, honestly, a mistake preserved by tradition. William Herschel, the astronomer who also discovered Uranus in 1781, coined the term in the 1780s because through the telescopes of his era, these glowing shells of gas had the same soft, rounded, faintly greenish appearance as a distant planet. He wasn't wrong about the resemblance. He was wrong about what he was looking at, and so, for the better part of a century, was everyone else. It took until 1864 for the mistake to be corrected properly, when the English astronomer William Huggins pointed a spectroscope, a device for splitting starlight into its component wavelengths, at one of these objects and found something no ordinary star produces, a spectrum of a small number of sharp, isolated emission lines, rather than the broad, continuous glow of a stellar surface. That told Huggins, correctly, that he wasn't looking at a dense ball of gas like a star at all, but a thin, glowing cloud, lit up from within by something small and intensely hot at its center. There is no planet involved at all, and hasn't been since Herschel first misread one. What's actually there is the exposed, superheated remnant of a dying star lighting up the gas it recently expelled, making it glow the way a neon sign glows, through ionization rather than reflection. The Ring Nebula, one of the most photographed objects in the night sky, and one of the 4 objects Herschel's era first catalogued this way, sits roughly 2,500 light-years from Earth, a genuine planetary nebula, glowing gas around a white dwarf that used to be an ordinary sun-like star. For context, this final glowing stage doesn't last. Planetary nebulae are visible for something like 10 to 50,000 years before the gas disperses too far and thins too much to keep glowing, which sounds like a long time until you set it beside everything that came before it. 10 billion years on the main sequence, hundreds of millions more across the subgiant and red giant stages, another 100 million in core helium burning, roughly 200,000 more churning through the AGB's thermal pulses. The planetary nebula phase is a coda to a coda, a brief visible flourish at the very end of a process that took most of the age of the universe to unfold. Laid end to end, if you compressed the Sun's entire main sequence lifetime down to a single ordinary year, the subgiant and red giant stages combined would occupy roughly the final month. The AGB phase would be over within the last few hours of the final day, and the visible planetary nebula, the part any nearby civilization could actually point a telescope at and watch, would last only the last few minutes before midnight. I still find myself checking this figure whenever I read it, because it never stops feeling wrong. After everything, after 10 billion years of steady hydrogen fusion and a few 100 million more of increasingly frantic shell burning, the visible farewell, the part any nearby observer could actually watch and photograph, lasts about as long as human civilization has existed. Less, in some cases. The slow parts of a star's life are almost incomprehensibly long. The dramatic parts are almost embarrassingly brief. What's left, once the nebula has drifted away and faded, is the only piece of the Sun that will still be recognizably present, in some form, for the rest of the universe's future, a small, dense, extremely hot core, no longer capable of fusion, radiating away the heat it has left. Roughly half the Sun's original mass will have gone the other way by then, scattered outward into the interstellar medium as an expanding, thinning cloud of hydrogen, helium, and the carbon and oxygen manufactured along the way, eventually mixing into whatever gas clouds happen to drift through that same patch of the galaxy over the following millions of years. Some fraction of that material may, eventually, in some future gas cloud, some future collapse, become part of a new generation of stars. That's not speculation. It's how most of the heavier elements already in the Sun and Earth got here in the first place, borrowed from stars that went through this same sequence long before the Sun existed. That object has a name too, and it's the one this whole video has been circling since the opening line. But before getting to what that object actually is, and what happens to it over the truly long term, it's worth pausing on something that gets lost in most tellings of this story. What any of this looks like from somewhere else entirely, if there were anyone watching this happen to a star like the Sun from a nearby, undoomed world, the way we are watching it happen to Mira right now, tonight, from ours. What's left, once the planetary nebula has drifted off and faded from view, is the object this entire video has been walking toward since the very first sentence. It's called a white dwarf, and it is, by a wide margin, the strangest thing the Sun will ever become. Start with the basic numbers, because they don't ease you in gently. A white dwarf holds something like half the Sun's original mass, compressed into a sphere roughly the size of Earth. Not a small star, not a large planet. A stellar corpse with planetary dimensions and stellar weight, which is a combination nothing in ordinary experience prepares you for. The density that results is difficult to even describe honestly without it sounding invented. A single teaspoon of white dwarf material would weigh about as much as a small car here on Earth's surface. Not because the atoms inside it are exotic, they're the same carbon and oxygen atoms as anywhere else. They're simply packed together at a density roughly 1,000,000 times that of water, close enough that ordinary atomic structure has essentially been crushed flat. What holds an object like that up against its own crushing gravity is not fusion. There isn't any left. What holds it up is a purely quantum mechanical effect called electron degeneracy pressure. And it's worth sitting with what that phrase actually means, because it's one of the odder true facts in all of physics. Electrons, according to a rule called the Pauli exclusion principle, cannot occupy the same quantum state as one another. Squeeze matter hard enough, and you eventually run out of new states for the electrons to occupy at low energy. They get forced into higher and higher energy states purely to obey that rule, and the pressure that results from all those electrons resisting further compression has nothing to do with heat. A white dwarf can cool for billions of years, and this pressure never weakens, because it isn't thermal at all. It's a direct consequence of quantum mechanics holding up a dead star the way a skeleton holds up a body, structurally, indifferently, without any furnace behind it. This kind of pressure produces a genuinely backward result once you compare white dwarfs of different masses. In an ordinary star, more mass means a bigger star. The sun is larger than a red dwarf, and a blue giant is larger still. In a white dwarf, it runs the other way entirely. Add more mass to a white dwarf, and gravity squeezes the electrons into a smaller volume to generate the extra pressure needed to hold that mass up. So a heavier white dwarf actually ends up physically smaller than a lighter one. It's a strange enough inversion that the first time you hear it stated plainly, it sounds like it must be a mistake. It isn't. Push more mass onto a white dwarf, and you get a denser, tighter, smaller object, all the way up to the Chandrasekhar limit, past which the electrons simply can't resist any further, and the whole arrangement fails. Gravity, at the scale of a star, is relentless. It never turns off, never takes a rest, never negotiates. For 10 billion years, the only thing standing between the sun's core and total collapse was the outward push of fusion, actively fighting gravity to a draw every second of every day. A white dwarf ends that fight, permanently, but not by winning it in the way you'd expect. It wins by finding an entirely different, non-negotiable law of physics, one that has nothing to do with energy production at all, and letting that law do the holding instead. The star stops working. The support structure doesn't. We didn't work any of this out from theory first. We stumbled into it by trying to explain a star that made no sense. In 1844, the German astronomer Friedrich Bessel, working from years of careful position measurements of Sirius against the background stars, noticed that Sirius, the brightest star in the night sky, wasn't moving in a straight line the way it should have been. It wobbled, very slightly, over years, tracing a faint, repeating wave across the sky rather than a clean path, as though something unseen were tugging on it gravitationally. Bessel correctly inferred a hidden companion star from the shape and period of that wobble alone, using nothing but Newtonian gravity and years of patient measurement, though he never lived to see the companion directly. It took until January 31st, 1862, for anyone to actually spot it. The American telescope maker Alvan Graham Clark was testing a brand new 18.5-inch lens, at the time the largest in the world, and pointed it at Sirius, mostly to check the quality of the glass. He noticed a faint pinprick of light sitting close beside it that nobody had recorded before. He hadn't set out looking for Bessel's predicted companion at all. He found it by accident, while doing something closer to quality control than astronomy. It took until 1915, when the American astronomer Walter Adams managed to capture a spectrum of that faint companion, for the real puzzle to appear. Sirius B was hot, hotter than Sirius A, in fact, by its spectrum, but it was also incredibly faint. The only way to reconcile a star that hot being that dim was if it were absurdly small, roughly the size of Earth, and once astronomers combined that size with the mass Bessel's orbital calculations had already demanded, the resulting density came out so extreme that, for a while, some physicists suspected the calculation itself had to be wrong. It wasn't wrong, it just needed physics that hadn't been invented yet. The explanation arrived a decade later, once quantum mechanics matured enough to describe how electrons behave when crushed together at extreme density. Ralph Fowler worked out the underlying statistics in 1926, and Subramanian Chandrasekhar, still a 20-year-old student at the time, sharpened that work further while sailing from India to England for graduate study, showing there was an upper mass limit past which electron degeneracy pressure would fail entirely, a limit of roughly 1.5 times the Sun's mass, beyond which a collapsing core has no choice but to keep collapsing into something even stranger. When Chandrasekhar presented the finished result to the Royal Astronomical Society in London in 1935, the same Arthur Eddington who opened this entire story with his lecture in Cardiff stood up immediately afterward and publicly dismissed it, calling it a result so absurd that nature surely wouldn't permit it. Eddington was wrong. Chandrasekhar's limit held up completely, was eventually confirmed by decades of subsequent observation, and won him the Nobel Prize in 1983, by which point Eddington had been dead for nearly 40 years. The Sun sits comfortably below that limit, regardless of who believed in it. Its eventual white dwarf will be stable, in the sense that nothing further is going to happen to it structurally for the remainder of cosmic time. Sirius B itself, the very star that forced this whole discovery into existence, still gets used today as a calibration point for exactly this kind of prediction. Modern measurements put its mass at just under the Sun's own, roughly 98% of it, packed into a sphere barely larger than Earth. Astronomers have used stars like it, alongside white dwarfs, found sitting inside star clusters whose ages can be independently measured, to build what's called an initial to final mass relation, a direct, observationally calibrated map from how massive a star started out to how massive its white dwarf remnant ends up being. For a star with the Sun's starting mass, that relation predicts a white dwarf weighing somewhere in the neighborhood of half the Sun's original mass, close to Sirius B's, arrived at not by pure theory this time, but by actually weighing the remnants of stars whose birth weights are already known. Theory and direct measurement converging on the same number from two completely different directions. If you have fallen asleep to this channel before, welcome back. And if you haven't, the object we started this whole video with, the small, dim star with nothing left burning inside it, sitting quietly among billions of others, is not a metaphor for anything. It's a real, physically ordinary outcome for a star of the Sun's mass, first stumbled into by astronomers trying to explain a wobble in Sirius's motion nearly 2 centuries ago, and eventually explained by physicists working out rules that apply just as cleanly to a teaspoon of matter as they do to an entire star. There's a further wrinkle to what happens inside a white dwarf that wasn't confirmed until remarkably recently, and it changes the texture of that carbon-oxygen interior in a way most descriptions skip past. As a white dwarf cools, over billions of years, the core doesn't stay a fluid indefinitely. Once the interior temperature drops to somewhere around 10 million degrees, still unfathomably hot by any everyday standard, but cold by the standards of what it used to be, the carbon and oxygen ions inside begin to lock into a rigid, ordered lattice. The white dwarf's core crystallizes. This was proposed theoretically all the way back in 1968, and for 50 years it remained an untested prediction, because no instrument could measure the tiny effects it would have on a white dwarf's brightness precisely enough to check. That changed in 2019, when astronomers using the European Space Agency's Gaia satellite, which had been quietly measuring the precise distances and brightnesses of well over 100,000 white dwarfs scattered near the Sun, found exactly the signature the old prediction demanded: a pileup of white dwarfs sitting at a particular brightness, exactly where you'd expect a population of stars to bunch up if crystallization were releasing a burst of latent heat and briefly slowing their cooling down. The prediction held. Solid carbon and oxygen, arranged in crystal form, sit at the center of aging white dwarfs throughout the galaxy right now. This exact structure, a serious physicist would, without any exaggeration, describe using the word crystal, because that is the physically accurate term for what it is. That last part, the cooling, the almost unimaginable stretch of time it actually takes, is where the rest of tonight is headed. A white dwarf doesn't do anything, in the active sense of that word, for the rest of its existence. It doesn't fuse, it doesn't collapse further, it simply cools, radiating away the heat left over from everything that came before, the way a dying ember keeps glowing long after the fire itself has gone out. What makes this stage worth dwelling on isn't drama, it's scale. The numbers involved in that cooling are long enough to make everything discussed so far, 10 billion years on the main sequence included, look almost brisk by comparison. The cooling itself doesn't proceed at a constant pace either, which is worth knowing before the numbers start piling up. A young white dwarf, fresh off its planetary nebula, loses heat quickly at first, simply because it starts out so much hotter than its surroundings that the temperature difference driving the radiation is enormous. As it cools, that difference shrinks, and the rate of further cooling slows along with it, the same basic principle that makes a cup of coffee lose its first 20 degrees quickly and its last 20 degrees painfully slowly. Stretch that principle across a body with the thermal mass of an entire star, though, and the slow final stretch isn't measured in minutes. It's measured in spans of time that make billions of years feel like the fast part. A newly formed white dwarf starts out ferociously hot, often above 100,000 degrees at the surface, hotter than the sun is right now, despite being a stellar corpse rather than an active furnace. Within about 2 billion years, that surface temperature has dropped to somewhere around 8,000 degrees, roughly what the sun's own surface measures today, and the white dwarf's brightness has already faded to a small fraction of what it started at. It keeps going from there. Around 5 billion years after formation, the entire carbon-oxygen core, the crystallization discussed a moment ago, has finished. The whole interior, not just a shell of it, has locked into solid crystal. One astronomer, doing the arithmetic on what that solid core actually amounts to, given its composition and mass, described the result plainly as a diamond in the sky, weighing in at something on the order of 6 billion trillion carats. It's a strange, almost absurd way to put a real number into words, and it happens to be accurate. For context, none of this is speculative extrapolation dressed up as fact. White dwarfs cooling on exactly this schedule are how astronomers date some of the oldest structures in the galaxy. Globular clusters, dense, ancient swarms of stars that formed near the very beginning of the Milky Way's history, contain white dwarfs whose current temperatures can be measured directly and run backward through the known cooling physics to estimate how long they've been cooling. The cluster called M4, one of the closest globular clusters to Earth, at around 7,000 light-years away, has had its age pinned down this way to somewhere around 12 to 14 billion years, consistent with independent estimates of the galaxy's age from entirely different methods. When the Hubble Space Telescope imaged M4's white dwarfs directly in the 1990s, the faintest ones detected were putting out roughly as much light as an ordinary household bulb would if you moved that bulb out to the distance of the moon, a genuinely difficult observation that only became possible once space-based optics improved enough to separate such faint points of light from everything around them. The sun's eventual white dwarf will, billions of years from now, be exactly the kind of object some future observer could use for precisely this purpose: a slow, honest clock built out of nothing more than heat, leaving a dead star at a calculable rate. None of this happens to an empty stage either. Jupiter and Saturn are expected to survive the entire process: the red giant swelling, the mass loss, the planetary nebula, all of it, still in orbit once the white dwarf settles into its long cooling. As the sun loses roughly half its mass along the way, its gravitational grip loosens, and computer simulations of the outer solar system's future show Jupiter and Saturn drifting further out in response, eventually settling into a stable rhythm where Jupiter completes 5 orbits for every 2 of Saturn's. This isn't pure guesswork about our own system specifically. In 2021, astronomers using a gravitational microlensing technique found direct evidence for exactly this kind of survival elsewhere. A planet roughly the mass of Jupiter, in a Jupiter-like orbit, quietly circling a white dwarf that used to be an ordinary sun-like star. It was the first confirmed case of a planet caught having survived its star's death, essentially intact, sitting far enough out to escape the worst of the swelling and mass loss. Exactly the kind of fate researchers expect for Jupiter and Saturn once the Sun follows the same path. The Sun will die. Some of what orbits it, it turns out, quite plausibly won't. Push the timeline further still, past 15 billion years, further than the current age of the universe itself, and a white dwarf's surface temperature has dropped to a few thousand degrees. Its light faded to 100,000th of what the Sun currently puts out. At this point, it would appear, to any observer nearby, as barely more than a faint red ember, difficult to distinguish from the surrounding dark, without instruments built specifically to catch what little it still emits. This isn't the finish line, though. It's simply as far as the universe has had time to go so far. The actual endpoint, the theoretical object a white dwarf eventually becomes, once every last trace of heat has radiated away, has a name: a black dwarf, cold, dark, radiating nothing meaningful at any wavelength. And here is the detail that tends to surprise people the most, once they hear the actual number involved. Nobody has ever seen one, anywhere, in the entire observable universe, and current physics says nobody ever will, not because they're rare or hard to spot, but because none has had time to form yet. The universe is roughly 13.8 billion years old. The theoretical cooling time required for a white dwarf to reach true black dwarf status is generally put at somewhere on the order of a quadrillion years, a number so far past the current age of everything that comparing the two isn't really a comparison at all. It's closer to comparing a single human heartbeat to the entire span of recorded history and then adding several more histories on top. Even that number carries a caveat worth being honest about, because it's one of the genuine open questions tucked inside this otherwise well-settled physics. The standard estimate assumes a white dwarf loses heat only through its own leftover warmth radiating away, with nothing topping it back up. But some researchers have pointed out that if dark matter particles exist in the form some theories predict, weakly interacting particles that occasionally collide with ordinary matter, a white dwarf drifting through a sufficiently dense patch of the galaxy's dark matter halo could receive a slow, continuous trickle of extra heat from those collisions, enough to keep it slightly warmer than pure cooling physics alone would predict, for spans of time that dwarf even the quadrillion-year estimate. Nobody knows yet whether this actually happens, because nobody has confirmed what dark matter is made of in the first place. It's included here honestly, as an open question, not a settled addendum. The true cooling time might be exactly what the simple physics predicts, or it might be longer still, depending on a piece of physics we haven't nailed down yet. If you have fallen asleep to this channel before, welcome back. The Sun's white dwarf, on the day it forms, will already be older in one sense than everything that has ever happened to it, because it will have already used up every mechanism it has left for changing. From that point forward, there is nothing left to do but cool, slowly, on a timescale that makes the current age of the universe look like a single early chapter in a much longer book, one where every subsequent chapter is quieter than the last. Picture it directly, for a moment, the way the title of this video asked you to at the very start. Somewhere out among the ordinary stars, 5 or 6 billion years from tonight, there will be a small, dim, unremarkable point of light where the Sun used to be, radiating the last of a warmth it generated 10 billion years earlier, indistinguishable at a glance from any other aging white dwarf scattered through the galaxy. Nothing about it will announce what it once was. No observer encountering it fresh would have any particular reason to suspect that a civilization once measured its output down to the watt, argued about its age for a century, and organized an entire calendar around its rising and setting. It will simply be one more star among billions, exactly as promised. If you could somehow stand on one of Jupiter's surviving moons at that point in the far future and look back toward what used to be the center of your solar system, you wouldn't see the familiar warm disk that currently lights every clear sky you've ever known. You'd see a single hard point of light, fainter than it is tonight, offering warmth to nothing in particular anymore, orbited by whatever outer planets managed to hang on through everything that came before. The days of a bright, generous daytime sky would already be an old memory by then, assuming anyone was still around to hold one. That's not a bleak note so much as an honest one. It's simply what the physics says happens to almost every star like this one, given enough time, including yours. That quietness, the specific kind of stillness that a fully dark, fully cooled stellar remnant would represent, is worth sitting inside for a moment, because it says something about where the rest of the universe is actually headed, not just the sun. Everything described so far about the sun is, in a very real sense, not really about the sun at all. It's about almost every star you can see on a clear night. Something like 97% of all the stars in the Milky Way, by current estimates, are following some version of this same script: main sequence, subgiant, red giant, helium flash, asymptotic giant branch, planetary nebula, white dwarf, and then the long, slow cooling that follows. Only the most massive stars, a small minority, are headed somewhere more violent, towards supernovae and neutron stars and black holes. The overwhelming majority, the quiet stars, the ordinary ones, the ones like the sun, are all walking this same path, at their own pace, on their own schedule, scattered across roughly 100 billion stars in this galaxy alone. That's worth letting settle for a moment. The fate described across this entire video isn't a special or unusual one. It's closer to the default. Wherever you look at the night sky and see an ordinary point of light, warm-colored, unremarkable, not obviously violent or strange, you are very likely looking at a star somewhere on this same road, some further along than the sun, some earlier, most of them fusing hydrogen quietly, the way the sun is doing right at this moment. All of them eventually arriving at some version of the same small, dense, cooling ember. There is something almost companionable in that, if you let it sit long enough. The sun isn't singled out for this fate. It isn't unlucky or unusual or facing something the rest of the galaxy has been spared. It's simply doing what nearly every star its size has always done, following a script written by nothing more mysterious than its own mass. The same script billions of other stars in this galaxy are following at this exact moment. Some nearer the beginning, some much nearer the end, all of them quietly indifferent to whether anyone happens to be watching. While all of this is unfolding for the sun specifically, something considerably larger is happening around it. For decades, Hubble Space Telescope measurements of Andromeda's motion suggested the Milky Way and Andromeda, our nearest large neighboring galaxy, were on a certain collision course, expected to meet roughly 4 billion years from now and fully merge within about 6. More recent analysis, incorporating additional galaxies in the surrounding cluster, whose gravity also tugs on the outcome, has revised that certainty down to something closer to a coin flip. Current estimates put the odds at roughly 50% that the two galaxies actually merge within the next 10 billion years, rather than passing near each other and drifting apart. It's a genuinely open question, and worth stating as one, rather than as settled fact. But NASA's own visualizations, built from the scenario where the collision does happen, describe the change in unusually specific terms: Right now, Andromeda is a faint smudge in the night sky, several times the width of the full moon if you know exactly where to look. In roughly 2 billion years, that smudge would already look noticeably larger. By 3¾ billion years, it would fill a significant portion of the sky outright, its gravity visibly warping the shape of the Milky Way's own disk. Collide is the dramatic word for what might come next, though the reality, if it happens, is far gentler than it sounds. Stars are so far apart, even within a crowded galaxy, that individual collisions between them are essentially not expected to happen at all. What actually merges is the two galaxies' overall shape and structure, their spiral arms distorting, stretching, and eventually blending together over the course of a few billion years into a single larger galaxy some astronomers have taken to calling Milkomeda. The Sun, wherever it happens to be in its own life cycle when this starts, would be swept along for the ride, its position relative to the galactic center shifting as the whole structure reorganizes itself, without any individual star needing to physically strike another. There's a genuinely strange coincidence buried in the timing here, assuming the merger happens at all, one that's easy to miss unless you line the two timelines up directly. The Sun's slow departure from the main sequence and the earlier stages of a possible Milky Way and Andromeda merger sit in roughly the same handful of billion-year windows, two enormous, largely unrelated processes, one stellar and one galactic, happening to occupy the same stretch of cosmic time almost by chance. Neither event causes the other. They're not connected by any physical mechanism at all. They simply happen to be scheduled, by the ordinary unfolding of physics, into roughly the same era, which is either a coincidence or a reminder that roughly the same era, at these timescales, still spans hundreds of millions of years in either direction. The drift doesn't stop at the galaxy's edge either. Zoom out further, past any single star or single merger, and the same basic pattern that describes the Sun's fate describes, in outline, the fate of everything with mass in the universe. Stars form from collapsing clouds of gas. They spend most of their lives fusing hydrogen. They eventually run out, swell, shed their outer layers, or explode, and leave behind some kind of compact remnant. A white dwarf for stars like the Sun, something stranger for stars far more massive. Those remnants persist, cooling or otherwise sitting quietly, for spans of time that make the current age of the universe look brief. Meanwhile, the raw material for forming new stars, the hydrogen gas drifting between existing stars, is finite and shrinking. Each generation of star formation uses some of it up and returns only part of it to the surrounding gas. Eventually, on timescales that dwarf even the white dwarf cooling numbers already discussed tonight, the galaxy will simply run out of the raw material needed to make new stars at all. When that happens, whatever stars remain will finish their own individual lifespans and go dark, one by one, without replacement, and there won't be new ones forming to take their place. The galaxy won't disappear. It will simply stop producing light, gradually, one extinguished star at a time, the same quiet ending currently in progress for a single star, playing out instead across every star that has ever existed. This isn't controversial physics, and it isn't imminent. The timescales involved make even the Sun's 10 billion years look almost immediate by comparison. But it is where the arithmetic leads, if you let it run all the way out. Cosmologists who study these very long timescales have given names to the eras this drift eventually passes through, and the names themselves are worth hearing, because they describe a future built entirely out of endings arriving in slow motion. The stretch of time we currently live in, when matter is organized into stars, galaxies, and the bright structures visible on any clear night, is called the stelliferous era, and by most estimates, it runs from roughly 1 million years after the Big Bang out to somewhere around 100 trillion years, a window that comfortably contains everything discussed in this video so far. After that comes what's called the degenerate era, the stretch once star formation has effectively ended, and the universe's remaining mass sits locked up almost entirely in white dwarfs, neutron stars, and other stellar remnants, quietly cooling, doing nothing else, for a span of time that dwarfs the stelliferous era, the way that era dwarfs a single human life. Even matter itself may not be permanent on these timescales. Some physical theories predict that protons, the particles at the heart of every atom, eventually decay, with a half-life so long, somewhere around 10,000 trillion years by some estimates, that it makes every other number in this video look almost countable by comparison. Whether protons actually decay at all remains unconfirmed. No experiment has ever detected it happening. It's included here as exactly what it is, a genuinely open, unresolved question in physics, not a settled fact, offered honestly rather than smoothed over. None of that changes anything about tonight, or about the sun as it currently is. Unremarkable, stable, roughly halfway through a fuel supply it has been drawing down steadily since before there was an Earth to orbit it. What changes is the frame around it. The sun's story, spooled out over the last hour, from a young Arthur Eddington doing arithmetic in a lecture hall to a cooling white dwarf sitting quietly for longer than anything else discussed tonight has lasted, turns out to be one instance of a pattern the entire universe is following, at its own pace, star by star, galaxy by galaxy, for as long as there's fuel left to burn. There's no need to carry any of that as a weight. The timescales involved are so far beyond anything a human life, or a human civilization, or even the entire span of a species' existence could meaningfully touch, that worrying over them serves no real purpose. They're simply true, in the same distant, settled way that the age of a mountain range is true, or the slow drift of continents is true, facts that sit at a scale too large to press against any single evening. What's actually worth carrying out of all this is smaller and closer than any of the billion-year figures. The light landing on the Earth tonight, wherever it happens to be daytime, somewhere on the planet as you listen to this, began exactly the way described at the start of this video. Mass quietly becoming energy in a core the sun has been running since before anything alive existed to notice. That process is still ordinary. It's still stable. It has roughly as long left to run as it has already spent running, which, on any scale a person actually lives at, is functionally forever. So what happens when the sun becomes just another star? It stops being the center of anything. That's the honest, unglamorous shape of the answer this video has spent an hour and a half arriving at. Not a collision, not an explosion visible from across the galaxy. It simply runs out of what made it special to us specifically, the steady hydrogen fusion that happened to warm one particular rocky planet for a few billion years. And once that's gone, what's left behind is a small, dim, ordinary object doing exactly what the vast majority of stars in this galaxy eventually do. Indistinguishable from any real distance, from countless other white dwarfs scattered through the Milky Way, each one the leftover core of some other star that used to matter enormously to something, once. I keep coming back to one particular fact from earlier tonight, more than any other. The light currently reaching you, if it's daytime somewhere you know, left the sun's surface only minutes ago, but the energy behind that light began its actual journey inside the core up to 170,000 years earlier, bouncing through the sun's interior long before anyone alive today, or their ancestors, or their ancestors' ancestors, existed to eventually receive it. Every day you've ever lived under that light, the sun was already sending you something it had been holding onto since before human beings existed. It will keep doing that, reliably, for another 5 billion years or so, which is longer than complex life has existed on Earth so far. There's a particular unease that sat with me the longest, working through everything this video covers. It isn't the ending itself, it's how ordinary the ending turns out to be. No violence, no warning, just a star, quietly running its numbers down to zero, the way every star its size does, on a schedule that was fixed the moment it formed. Picture the object this video opened with one more time. Small, dim, sitting quietly among billions of other points of light, radiating away the last of a warmth it built up over 10 billion years of ordinary, unremarkable fusion. Nobody encountering it fresh would have any reason to suspect it once anchored a solar system, once had a name, once had a whole species that measured time by its rising and setting. It will simply be there, doing what stars like it do, for longer than anything else in this story has lasted. If you're still awake for this part, here's the handoff for tonight. Everything discussed here assumed the sun dies alone, on its own schedule, following its own physics. But most stars in this galaxy aren't alone. Most are paired with at least one companion, orbiting a shared center of mass, their fates tangled together in ways a single star's story can't capture. What happens when one star in a pair becomes a white dwarf first, while its companion is still burning, is a stranger and more violent story than anything covered tonight, and it's one for another night. Whatever tonight asked of you, the dark overhead asked nothing at all. Sleep. Nothing at all. Sleep.